Welcome, everyone. Today we're diving into the world of the periodic table, that incredible tool that organizes chemistry, from the elements we use every day to those that spark groundbreaking research.
Yeah, absolutely. It's crazy how a simple table can unravel the mysteries of matter, right? What really makes it so indispensable?
Totally. I mean, when you look at it, the periodic table shows you that the elements aren't just a random pile, but, they form families, each with trends that tell us so much about chemical behavior.
Indeed. Right. And historically, it all kicked off with folks like Dobereiner noticing triads, groups of three elements with similar properties. I love how he saw that the middle one was almost exactly halfway in atomic weight between the other two.
Yeah, that's a neat observation. Exactly. And then you have Newlands, who went on to propose the law of octaves, arranging elements by atomic weight and noticing that every eighth element echoed similar properties like the notes in a musical octave.
Oh, like nature's very own symphony. Absolutely, but it's interesting that Newland's idea was only valid up to calcium. It really highlights how even brilliant insights can hit limitations when applied broadly.
That's a point worth noting. Yeah, and then along come Mendeleev and Lothar Meyer. Mendeleev, especially with his daring prediction of elements that hadn't been discovered yet, leaving gaps in his table that were later filled by gallium and germanium.
Right, that predictive power is just phenomenal. It's like, imagine having a puzzle with missing pieces and confidently saying, hey, these pieces exist somewhere out there.
Exactly that. And later on, with Henry Moseley's work on X-ray spectra, we found out that it's not just about atomic weight, but about atomic number, which really deepened our understanding.
Yeah, it's a fundamental shift, isn't it? For sure. The shift to atomic number as the organizing principle is like swapping a blurry picture for high definition clarity. But let me ask, how do you see the role of electronic configuration in all of this?
Great question. Electronic configuration is the backbone of the structure here. Our table isn't just arranged by number, but it reflects how electrons fill up the s, p, d, and f orbitals. And this configuration exactly explains why elements in the same group behave similarly.
Yeah, I get that. So, in a way, it's like the table is a mirror showing us the quantum world, each block of elements representing a different flavor of electron filling.
Right on. For example, S block elements, those alkali and alkaline earth metals, have a single or a pair of electrons in their outer shell. And as you move to the P block, you see elements with outer configurations varying from Ns2np1 up to Ns2np6, culminating in those inert noble
That
gases.
makes perfect sense. And then there are the transition elements in the D block, right? Which give us that colorful chemistry and variable oxidation states.
Yeah, like a painter's palette. They even bridge the gap between the highly reactive metals and the less reactive ones. And don't forget the F block elements, the lanthanoids and actinoids. They're fascinating, especially with their complex electron configurations and often unstable radioactive nature.
Totally a real marvel. Speaking of marvels, I noticed that the table also adapts over time. The modern periodic law bases itself on atomic numbers rather than atomic weights. It's like the table evolved along with our understanding of the atom.
Spot on. And with the introduction of artificially made elements, those with atomic numbers above 100, the table had to get even more systematic. I mean, you have the IUPAC nomenclature system with its numerical roots.
Yet the naming scheme, right? Exactly. So element 120, for instance, is temporarily called unbenyllium. It's a cool system because it avoids controversies surrounding discoverers trying to claim credit.
Right? And that system ensures consistency. Oh, and another interesting angle is how periodic trends like atomic radius, ionization energy, and electronegativity gracefully change across periods and down groups.
Yeah, like the atomic radius generally decreases across a period due to enhanced nuclear pull. And conversely, as you go down a group, the atomic radius increases because the electrons are getting further away, with more electron shielding, right?
Exactly. And these trends explain why, say, alkali metals are so reactive compared to the halogens on the other side of the table. It's all about how tightly or loosely the electrons are held.
And that ties back to the effective nuclear charge, doesn't it? It sure does. But I have to challenge one point. Sometimes I feel the descriptions of trends oversimplify things, like ignoring exceptions such as helium in the S block. What do you think?
You raise a valid concern. Helium, for example, technically sits in the s block due to its configuration, just a filled 1s orbital, but its chemical behavior aligns more with the p block noble gases. It's a nuance that shows even our best
Yeah,
classifications
that's
have their
exactly what I was
quirks.
thinking. I appreciate how those nuances bring life to chemistry. After all, nature rarely fits perfectly into our neat boxes, yet these systems help us navigate that complexity.
Totally, it's like each classification is a model, a simplified version of reality that gets more accurate as we learn more. And speaking of models, the long-form periodic table is especially interesting. It neatly categorizes elements into groups numbered 1 to 18 and even accommodates the lanthanoids and actinoids in separate panels.
Right, it's more comprehensive that way. Yeah, and considering the sheer number of elements now, from just 31 in the 1800s to 118 known today, the periodic table stands as a testament to the growth of our scientific knowledge.
Absolutely. And it's not just a static snapshot, it evolves with every new discovery. The ongoing synthesis of super heavy elements reminds us that our table, much like our understanding, is always a work in progress.
Oh, for sure, that's the beauty of science, right? Definitely. And with every tweak, like the shift from relying on atomic weight to atomic number, we see how experimental advances shape our theoretical frameworks. It's a great reminder that science is dynamic and ever adaptive.
Right. The connection between quantum numbers, electron configurations, and periodic trends is essential. Knowing that an element's position dictates its properties makes the whole structure both elegant and highly practical for predicting behavior.
Yeah, it's like a cheat sheet for understanding matter. And let's not forget about the practical applications, from predicting reactivity in labs to guiding new materials research. The periodic table isn't just historical, it's an everyday tool for scientists.
Absolutely, it's the cornerstone of both education and research. One really fun analogy is thinking of the table as a giant cookbook for matter. Instead of recipes, you have periodic trends that suggest how elements will interact, mix, and combine to form everything from water to cutting-edge
Haha, yeah, a
superconductors.
recipe for everything. I love that imagery. It really brings home the idea that the periodic table is both systematic and creative. And with each new element or trend uncovered, the recipe book gets richer and more detailed.
Totally. And even though we've explored so many facets, historical development, electronic configuration, classification into blocks, periodic trends, and modern nomenclature, the fundamental message remains. Understanding the periodic table is key to unlocking
Right,
the
it's the
chemistry
ultimate
of the
guidebook.
universe. Welcome to our deep dive into periodic trends and properties of elements. Today, we're exploring how ionic radius, ionization enthalpy, electron gain enthalpy, and electronegativity all
Yeah,
interconnect in the world
absolutely.
of chemistry.
I'm really excited because these trends really shape our understanding of the periodic table. For instance, the concept that a cation is smaller than its parent atom while an anion is larger. It's pretty fascinating, right?
Exactly. It's like um, when you remove an electron, you drop some of the electron repulsion, so the electron cloud contracts. And conversely, if you add an electron, the extra electron repulsion causes expansion.
Right. And that idea is backed up with some concrete examples, if I'm not mistaken. Take fluoride, for instance. Its ionic radius is about 136 picometers compared to the atomic radius of fluorine, which is around 64 picometers.
Yes, and then you have sodium. Sodium's atomic radius is about 186 picometers, while its cation, Na+, shrinks down to roughly 95 picometers. It clearly shows how losing electrons makes a huge impact.
Interesting enough, when we consider isoelectronic species like O2, F, Na+, and Mg2+, all having the same number of electrons, their sizes vary due to differences in nuclear charge, right?
Exactly. It's like the more positive the nuclear charge, the tighter the grip on the electrons, making for a smaller radius.
Mm-hmm.
So magnesium ion, having a higher charge than, say, fluoride, ends up being considerably smaller.
That reminds me, there was that problem comparing Mg, Mg2+, Al, and Al3+. The conclusion was that magnesium is the largest, while Al3+ is the smallest, due to increased ionization effects. Am I right?
Absolutely, the atomic radii decrease across the period, and when you convert an atom to a cation, it shrinks because it has fewer electrons repelling each other, while the nuclear charge stays constant.
Yeah. Now, switching gears a bit, let's talk about ionization enthalpy. It's defined as the energy needed to remove an electron from a neutral atom in its ground state. And guess what? Energy is always required to pull an electron out, so these values are always positive, right?
Exactly. And what's more, each successive electron removal becomes more challenging, which means the second ionization enthalpy is higher than the first, and the third is even higher than the second.
I remember that the trends show that ionization enthalpy increases as you move across a period, mainly because the effective nuclear charge increases while the shielding stays almost the same.
Yes, and when you go down the group, the outermost electrons are further away from the nucleus, increasing the shielding. So it takes less energy to remove that electron.
Right. Now, here's something I find really neat. The exceptions to these trends, like how boron's first ionization enthalpy is a shade lower than beryllium's, right?
Good point, it's fascinating. Despite boron having a higher nuclear charge, its ionization enthalpy is lower, because the electron removed is in a p orbital, which is more shielded compared to the s orbital in beryllium.
Yeah, that's a great nuance. And that nuance is also visible in oxygen versus nitrogen, right? Because oxygen's electron-electron repulsion in its 2p orbitals makes it easier to remove an electron compared to nitrogen.
Exactly. It's like the extra repulsion in oxygen rearranges our expectations a bit. Even though oxygen has a greater nuclear charge, the increased repulsion from having paired electrons in a p orbital lowers its ionization enthalpy compared to nitrogen.
Indeed. Now, moving on to electron gain enthalpy, things get even more interesting. The addition of an electron can either release energy or require energy, depending on the element. Isn't that right?
Absolutely. For halogens in group 17, they release energy and hence have negative electron gain enthalpies because they achieve the noble gas configuration. But for noble gases, it's a different story. The added electron must go to a higher energy level, meaning energy is consumed, resulting in a positive electron gain enthalpy.
Yep. I also recall there's a trend where electron gain enthalpy becomes more negative across a period, but it gets less negative as you go down a group. However, exceptions like oxygen and fluorine show that adding an electron to a smaller orbital can lead to significant electron-electron repulsion.
Yes, exactly. For oxygen and fluorine, the added electron enters the tight confines of the N2 level, so self-repulsion is much greater. In contrast, for elements with electrons in the N3 level, the added electron experiences
Right on.
less repulsion.
It brings us naturally to electronegativity. Now, electronegativity is a qualitative measure of an atom's ability to attract bonding electrons. And although it isn't measured directly, there are scales like the Pauling scale that give it numerical values.
Exactly, it's like how much an atom pulls the electrons in a bond. Fluorine tops the chart at 4.0 on the Pauling scale because it's incredibly electronegative, while elements further left on the periodic table score much lower.
And here's the connection. It trends similarly to ionization enthalpy. As you move across a period, atomic radii decrease and electronegativity increases. While moving down a group, the increase in atomic size leads to a drop in electronegativity.
That's spot on. These properties together explain why, for example, non-metallic properties increase across a period while metallic character decreases.
Yes. There's also an interesting interplay in terms of valence or oxidation states, right? The number of available electrons for bonding, often equating either to the outer electrons or to 8 minus that number, influences the types of compounds elements form.
Absolutely. And you see these trends in compounds, such as silicon forming CyBr4 with bromine because of its tetravalency, or aluminum and sulfur forming Al2S3.
Yeah, indeed. I find the discussion on anomalous properties of the second period elements particularly intriguing. Lithium and beryllium, for example, display some unique behaviors compared to their heavier congeners, largely due to their small size and high electronegativity.
Right, it's like, these elements don't quite follow the standard rules. Instead, they sometimes form compounds with more covalent character than the rest of their group.
Absolutely. And that diagonal relationship, where lithium behaves a bit like magnesium and beryllium like aluminum, is a fascinating outcome of these atomic factors, such as the available orbitals and effective nuclear charge, isn't it?
Yes, definitely. The limited availability of valence orbitals in the first members of these groups restricts maximum covalency, whereas later elements can expand their valence shells thanks to additional orbitals like
Aha.
3D.
Before we wrap up, I want to challenge one point. While these trends are so neat in theory, aren't there exceptions, especially among transition metals, where the changes in atomic radii are minimal and ionization enthalpy trends aren't as clear-cut?
That's a valid critique. Transition metals do indeed complicate the picture. Their d orbitals introduce less dramatic changes in radii, and their electron interactions balance out the simple trends we see in s and p block elements.
Yes, that's a good observation. So, in summary, we've seen that periodic trends like ionic radius, ionization, and electron gain enthalpies, as well as electronegativity, all tie back to electronic configuration and effective nuclear charge, influencing everything from atomic size to chemical reactivity.
Exactly. It's a remarkable tapestry of trends where each property interweaves with the others to dictate how atoms behave chemically. From the basic contraction of a cation to the unique bonding in second-period elements, everything is interrelated.
Totally. And looking at the periodic table as a whole, these trends not only help us predict chemical reactions but also give insights into why certain compounds form the way they do, like the difference between basic, acidic, and amphoteric oxides.
Right? For example, oxides at the extreme left, like Na2O, are basic, while those at the extreme right, like Cl2O7, are acidic. In the middle, you might find amphoteric behavior, illustrating a balance between electron donation
Absolutely.
and acceptance.
This discussion really underscores how deeply the periodic law runs in determining chemical behavior, right?
Yes, it really does. It's like every property we've discussed today is a consequence of the underlying electronic configurations built into the periodic table. And by unpacking these periodic trends, we get to see why chemistry at its core behaves the way it does.
Yeah, indeed. Thanks for the engaging chat on such a rich topic. It's been truly enlightening to break down these trends and see how interlinked they really are.
Thank you as well. It's been a pleasure diving into the nitty-gritty details. Until next time, keep exploring the wonders of chemistry.
Absolutely. Cheers.